We have now a talk by Olga Turanova, who is assistant prof at the Department of Mathematics of Michigan State University. And she will talk about a particle method for degenerate diffusion and applications to robotic swarming. Thanks, Olga.
Thank you. Thanks for the introduction. And I wanted to thank the organizers for inviting me and for allowing folks to speak remotely. Yeah, I'm very happy to be participating. Okay, great. So let me start the talk. So first, let me say that this is all joint work with Katie Craig and Karthik, along with Skuti and Matt Haberland. Okay. So first, I'll talk about like the PDE that we're going to be looking at. I'm going to have in mind this application to robotic swarming. So I'll tell you a little bit about that. Then I'll tell you the numerical method that we study. I'll give you some ideas from the proofs. I'll tell you a little bit more like how do we apply this to the swarms, and then we'll conclude. Great. So we're gonna pick some nice domain omega in RD and some coefficient rho bar that goes from omega to R plus, and both are nice. I don't want to say now how nice. So this is the PDE that we're looking at. So notice it's time dependent degenerate diffusion type PDE. So there's the coefficient rho bar. So it's dt rho minus divergence of rho grad rho over rho bar. And it's coupled with this boundary condition, although during the talk, I'm not actually going to talk about the boundary condition at all. But I put it here for you guys to see. So notice that if this coefficient rho bar is just 1, then this diffusion term becomes just rho grad rho, which is a half divergence of grad rho squared, which is of course a half of the Laplacian of rho squared. So the reason I put this up is to show that this PDE it's an inhomogeneous porous medium type equation. In other words, if you want to look at the porous medium type equations and you want to put some inhomogeneity somewhere, this is one spot to put it in. So notice, and this is going to be important for our discussion about robots. So for large times, the solutions rho of xt converge to this rho bar. So you can see this formally just by imagining this term equals 0. And there's also like factual results that say this and even say how fast that happens. Okay, so let me talk about the robots. And I hope this will also, so we seek to pollinate a field of flowers using robotic bees, which is actually a problem that I have heard of in, I don't know, context outside of math. So each bee, what can it do? Each robotic bee, I should say, can sense whether it's over a flower, can sense whether there are other bees nearby, and can change its velocity based on this info. Bees can't communicate with each other or with a central hub. So how do we model this? So we have some omega, say in R2, which represents the field. Here, we take a rho bar, which represents, the rho bar here represents the distribution of the flowers in omega. And we seek to be able, we want to make like an algorithm for controlling the bees where rho bar is not known a priori. Because if it were, that would be, there wouldn't be much to do. You could just direct the bees. But yes, so rho bar is not known to the bees. And the goal is to get the bees to come to the flowers. In other words, we want the density of the swarm to be like rho bar. So let me talk about the numerical method that we introduced. So there's our PDE again. So solutions to this guy are Wasserstein gradient flows of the following energy. So the energy of rho is a half integral on omega, rho over rho bar d rho. And so formally, this is evident from like taking the functional derivative of E and seeing that it corresponds to the correct term in the PDE. And rigorously, this is true under an additional assumption on rho bar, which I'll talk about in a little bit. So the main idea of the numerical method, so remember our goal is to produce a deterministic particle numerical method. So to approximate the energy E in a way that ensures that particles remain particles. For example, this PDE itself is a diffusive equation. If you start with initial data, a sum of Dirac masses, they don't stay that way. And this originates from Carrillo, Craig, and Pattacini from 2019, who studied the case of constant coefficients. So how do we approximate this energy? So there's our energy again. So rho over rho bar d rho. And so I'm going to be conflating measures with their density. So in particular, when we, so all measures that are relevant here have density, and I conflate measure with density. So I can write the energy like this. So I'm going to be talking about how we produce this regularized energy that I mentioned in the previous slide. We take a modifier like the Gaussian, or say the Gaussian, which is what we actually use when we implement this method, which I'll show you later. And one of the properties that we wanted to enjoy is that it can be written as a convolution of two other modifiers that also have certain properties. But if you want, you should think of this guy as the Gaussian, and actually it can be written as this convolution of two Gaussians. So this is what we define. We define the energy of rho to be the integral of rho convolved with zeta epsilon, where zeta epsilon is like the usual rescaling of our guy zeta squared over rho. And if you notice, this is just the energy, our original guy, at rho convolved with zeta. In fact, there's several ways to define an energy E epsilon that approximates E in this sort of way. And this is actually different from the way it's defined in Carrillo, Craig, and Pattacini, even for rho bar being one, I believe. But anyway, so we're really going to rely on the gradient flow structure here. So the gradient flows of this guy are solutions of this continuity equation. And we want to, let me just compute this functional derivative explicitly. The functional derivative of E epsilon with respect to rho is this guy. So zeta convolved with rho over rho bar. So it's so the key point of it and why this approximation is useful is that solutions to this continuity equation with particle initial data remain particles. So let me talk a little bit about this approximate continuity equation. So here's a lemma, which I'll write out in possibly too much detail, but bear with me. So I'm gonna use rho sub n epsilon to denote the, say, distributional solution to this continuity equation. which is the exact same one as on the previous page, with initial data a sum of n Dirac masses. So that's what the n corresponds to the n masses, and the epsilon corresponds to the epsilon I take for my modifier. Okay. There we go. So then for T positive, my solution remains a sum of Dirac masses. So they started at some locations xi of 0. They're now at some locations xi of t. And I'll tell you how these locations evolve. So these locations xi of t evolve via a system of ODEs associated to this continuity equation. And I'll write it out again explicitly for you guys to see. So there's some velocity, v epsilon, and that's given in this complicated way. So notice the velocity depends on the masses I started with and on the positions of the other particles as well in this particular way. And that just comes from looking at this term and sort of what happens when the rho that you have here is the sum of Dirac masses. Okay. Great. But maybe one key point is that if I start with the sum of Dirac masses, it stays the sum of Dirac masses. And moreover, there's an ODE that tells you how these masses evolve.
Sorry, Olga, one question. Sorry if I misunderstood, but earlier you said that rho bar was not known from the B's, and here you use rho bar, right? Or...
So that's a really great question. So let's see, where do I, oops, let me go back. There we go. So the rho bars, so the B's can sense the rho bar in their location and also nearby. So notice that if these zeta epsilons are Gaussian, so there's a little bit of discrepancy between the numerical method and the application to robots. So for this, if you want this zeta to really be a Gaussian, then they kind of do have to sense rho bar everywhere because the Gaussian doesn't have compact support. But in practice, because this guy is really, really tiny, far away from where the B is, they don't actually have to sense rho bar far away, just sort of see it nearby.
Okay, thanks.
Does that, yeah, okay. And I'll actually address this question probably again when I go back to talking about the robots.
Can I ask a quick question? Do you
Sure.
require the gradient of the modifier at the origin to be 0, or can you have interactions of a B with itself, like a drift?
I think that the modifiers have to be like, at least we studied radial modifiers.
Okay.
Yeah. Thank you guys for the questions. It makes me feel more like I'm actually there. So I really appreciate that. Thank you. Okay, let me continue. Okay. Oh my goodness. There we go. Okay, so let me just summarize the numerical method. So we have given some initial data rho 0, you discretize it into n particles, okay, by some whatever your favorite way, say. Then you let the particles evolve via that ODE system that I just wrote, where v epsilon is what was given there. And then I let rho n epsilon to be this moving sum. And then, so in order to get back a nice looking density, we consider blobs over each particle. In other words, let's consider rho twiddle of n epsilon, which is exactly this sum, except instead of being a sum of Dirac masses, it's that same modifier zeta epsilon, but centered at the point xi. And of course, this is zeta epsilon convolved with that sum. Great. And this guy is our approximate. I mean, you could think of either of the two rows with the twiddle or without the twiddle as the approximate solution. Great. But I think when I show the videos, or I'm sure that when I show the videos, it'll be this row bar that I show. Oh, great. Time for the videos. So let's see how I will pull them up on my computer. Okay, great. There they are. So here's the first video I wanted to show. So notice here, this green line is like the row bar, okay? Then these orange dots are the xi's, and the blue line is like the row and epsilon twiddle, okay? And we're gonna see, so one thing to look at, so my favorite part of these videos to look at is to see how the xi's move around. So how the points xi's evolve in time. So let's see. There they go. Oh boy. So notice that now they've kind of stopped. So the neat thing about this method, and also about maybe the application to robots, is that these guys kind of just figure out where to go. They go there and then they stop. And this is with 50 of these dots. Okay. So let me show the next video. So again, the orange dots are the positions of the particles or of the robots, if you want. And now we took the desired guy or the coefficient to be this discontinuous thing. So let's see how, and again, there's 50 of these xi's, and because there aren't so many of them, you can see how they move. So let's watch. So here it takes a little bit more time for them to settle in because the coefficient has this discontinuity. And notice it doesn't quite match up perfectly, but that's because there's 50 of them and this guy is discontinuous. So for this one, I want to show here, now I believe this is 200 robots or 200 particles. So there they go. Because there's more of them and sort of the blobs are thinner, they get closer to even the discontinuous guy. But this isn't, I like the other videos more because I like to see the blobs moving around, but here you can't really see that. Okay, so I think these videos hopefully give you an idea of what's going on with the method. Okay, so let me see. Great. Okay. So let me just state our results rigorously. So there's my collaborators, who's Craig, Olga, Smoothie, and Hammerland. So our assumptions on our coefficient is that it's C1 and bounded from above and strictly away from 0 on our omega. So the second assumption is that rho bar is log concave. So it's e to some v of x for some concave v. And we also make some assumptions on the initial data. So here's the theorem that that relates directly to the numerical method, which is that if let rho solve the PDEs and also take, I guess it doesn't say it here, but take so discretize your initial data into n particles. Then as epsilon goes to 0 and n goes to infinity, the rho and epsilon go to rho, and the rho twiddle go to rho twiddle and epsilon go to rho narrowly. Okay. And this follows, so the main work is to prove the second theorem, which says the following. So let rho epsilon be the Wasserstein gradient flow of E epsilon with initial data rho 0. Then the rho epsilon narrowly converge to something, rho, and that something is the gradient flow of E with that same initial data. So to go from the second theorem to the first theorem, you essentially just apply you just essentially add in the approximation of row zero by initial data and control the error. So the main work is to prove the second theorem. And that's what I'll talk about briefly on this slide here. Okay. So when rho bar is log concave, the energy E that we're working with is a standard internal energy. And we already know from the work of, say, Ambrosio, Gigli, and Savary, that the gradient flows of this E are well defined. So then we have to study next this E epsilon, which is this new approximate energy that we defined. We first want to study its convexity properties. So we show that this guy is lambda convex along generalized geodesics in Wasserstein space. And this lambda is negative and gets it gets bad as epsilon goes to 0. But that's still sufficient for us. And notice that this result doesn't require the log concavity assumption, which is kind of cool. So from bullet point number 2, we conclude that gradient flows for E epsilon are well defined. Then we show that E sub epsilon gamma converges to the energy E. So then to show the convergence of the gradient flows, we first obtain an estimate that's sort of like an H1 norm for gradient flows of E epsilon. So formally, you can get this by like manipulating the epsilon level PDE, like in the way that you manipulate PDEs to get estimates on norms. Rigorously, because we're working with the gradient flows and the PDE formulation is so weak, we use this flow interchange method of Max, McCann, and Savary. And interestingly, this also does not require the log concavity assumption. So then we use this to prove that the metric slopes of E epsilon converge to those of E. And by a general result of Sarfati, this is enough, along with the gamma convergence, to deduce that gradient flows of E epsilon converge to gradient flows of E. Great. So let me return to the robots for a minute. So remember, our goal was to get but I think you guys already know what I'm going to say, because based on your questions, the goal was to get the bees to come to the flowers. In other words, for the density of the swarm to be like our rho bar. So we take x0i to be the initial B locations, define xi of t to be the solutions of the same ODE system, and then let them evolve in that way and let rho twiddle be this blob guy. So here epsilon represents pollination radius, but also, as I said earlier, the sensing radius, where the bee can sense the values of rho bar and the presence of other bees. So for small epsilon, large n, and large t, so our approximate solution is like our actual solution, but if that's for small epsilon and large n, and then for large t, our solution is like rho bar. So therefore, we've achieved, at least in theory, our goal of getting our robot swarm to be like our desired density, or in other words, to get the bees to come to the flowers. So that's great. So future work, so let's see what I put. So rate of convergence, you can probably notice those quotes there. It would be really nice to quantify them. I think the T is pretty okay, but the other two, we don't know what to do. So numerically, we observe the convergence is of rate 1 over n, or better when things are when your density is smooth. So the second future work is to remove this log concavity assumption. And notice that it was not used, it was used in some parts of that outline I gave, but not in all of them. So there is hope. Plus our numerics seem to work very nicely, even without that, when rho bar isn't necessarily log concave. Great. So here I want to, this is great from the question that you asked. We want to see what happens if you use a compact mollifier. So to really make sure that the bees can only sense in a certain radius. And more general degenerate diffusion. That's also another interesting question. And maybe one other bullet point, which I don't think I put here, is so my previous slide about the applications to robotic swarming, it's pretty much from our imagination. It would be if you're interested in actually using this to control robots, there is a lot of work to be done. For example, seeing what happens with a compact mollifier, things like this. Maybe guessing these rates better if you really want to do applications. Okay, that's all I wanted to say. Thank you very much.
Thank you, Olga. Any questions for Olga?
Thank you. It's a very nice talk. So I have a question on the more technical side. So consider the n equal to infinity and epsilon equation, and then you said that you have the result that you let epsilon go to 0. There's convergence of gradient flow, but no convergence rate is given. So I'm thinking of another direction. Suppose you fix your epsilon and then you let t go to infinity. What can we say about the long-time convergence?
So for the epsilon equals 0 case, because this is like this known internal energy, like you can say things about in time convergence, like the Wasserstein norm between the solution at time t and the rho bar goes to 0. There's like PDE type work that can estimate like the KL divergence between those two. But I don't know what happens if epsilon is positive. So for the regularized guy, that's a good question.
Thank you very much, Olga. So I had a question about, thinking at the application with the flowers, right? So the flowers, they have a density macroscopic, but actually microscopically, they are actually deltas, right? So my question is, so is there a way to guarantee in some, so of course so in that case, you cannot observe rho bar, but you observe, a number of flowers that are in your radius. So is there a way to ensure in some way, that for every ball of radius, let's say epsilon, which goes epsilon is the parameter where the bee sees, there is, I don't know, at least one bee for every, I don't know, 2 flowers, or at least 3 bees for every 4 flowers, so something like that.
So I think that maybe this is a question of like, so of how big of an N do you need to pollinate this field? And I think that's really a question about like the rate of convergence. So I think that for like just from observing things, if your N is not too big, you still get a pretty good approximation. I don't know, and at least to me, I do really think of the flower density as some continuous thing, because like the way that the bees sense it, I mean, I would imagine one way to sense it is by maybe sensing like color or something like this. So you sense like where bushes are versus where brown ground is, and bushes are sort of greenish and brown ground is brown. Yeah, I actually so I started working on this from like from this robot's perspective with my co-author Hamberland, who had mentored like an REU where students actually had a robot and they used like a stochastic algorithm to get the robot to sense things and like go to swarm to go to the flowers. And there in that really real life implementation with like physical robot, it really worked to have it to have the row bar be like a continuous thing.
Two quick questions.
Thanks, Olga. It's a very interesting talk. So I have a question on the, can you comment on the computational complexity of this dynamics? I mean, the algorithm?
Well, I can comment on it. It's not, I gotta say, it's not the best because I put so many pauses in the slides. Let me go back to the slide. I want to find the slide where we write down the V epsilon explicitly. Okay, there it is. So notice that this V epsilon, there's a gradient and there's an integral. So I certainly would not say that it is cheap to compute, but I don't have more precise comments on that.
So here, this integral, how do you evaluate this integral? You use particles, right?
I'm sorry?
How do you evaluate this integral over there?
Oh, is Katie about to answer
I'm right
for
here.
me?
I'm just sorry since Olga has been kindly doing much of the heavy lifting on the theoretical side, and Matt and I have been working together a lot in the numerical implementation. So I will just comment that the integral here is something that can be pre-computed at the initial time. This is just pre-computed as a function of yi and yj. For example, for certain types of, think of zetas as a Gaussian. So yeah, sure, you have to we're assuming we know a lot about our mollifier. So maybe you even have a closed form expression for the gradient of zeta coming in. This is something you can choose. And then, for example, for simple choices of row bar, that integral actually has an analytic expression. For more complicated choices of row bars, for example, Olga showed in one of her simulations, or even the piecewise constant one, actually all of the ones she showed, there's an analytic expression for it. For more complicated choices of row bar, you would have to decide how to approximate that integral, but that's something that's done in initial time. So it doesn't, while it can, it's something that has to be done initially, it's not something that it factors into the computational complexity along the dynamics.
Thanks.
Thanks, Katie.
One last question, maybe the rest for the coffee break.
I'm sorry, I will keep it short. On one of the initial slides, you had a modifier, I think phi, which was the convolution of two of these zetas. And I'm not sure whether I missed the phi disappearing later or whether I just didn't see it anymore. And so I was wondering which role that played.
I think that I think that it doesn't play too much of a role. I think in future versions, I'll just remove that and leave the zeta. I think it's, yeah, I shouldn't have put that there. The reason
Okay, thank you.
I guess it does play a role maybe because we do take, when we implement them, we really do take both of them to be Gaussians. But in our results apply to a more general class where we have some assumptions on the zeta and some assumptions on the phi. So yes, thank you for pointing out that confusing point so I can fix it for future presentations.
Thank you.
Do you have a last question?
Yeah, I will make it shorter. So you have this energy that with the goal that you want to map row to row bar. So I wonder why this particular energy, or it was more PDE based, motivated because there's a nice PDE and that's happened to be this energy.
The PDE, I mean, sorry, the energy E or E epsilon? Or both?
I say E.
It was motivated by the PDE. And yeah.
Okay, thank you. Maybe we can have other questions during the coffee break, but thank you, Olga.
Thank you. Thank you for listening.